Miscellaneous exercise 1. First question. You are given a function f, which is fx equals to 10x plus 7. You know that this is a standard linear function from R to R, so it must be bijective, that we know. Now, what is the question here? We are asked to find a function g which satisfies this condition. Now, you recall, if any function g for a given function f satisfy this condition, fog and gof both are identity function, then your g must be inverse of f. So from definition you can say that, from definition we can say that g must be inverse of f. Inverse of f. So therefore we find g equals to f inverse. So it's a question, ultimately you get the inverse of f. So you know method, let fx equals to y, this is the procedure. Now put the formula for fx, that is 10x plus 7 equals to y. Make the x as a subject of the expression. So 10x equals to y minus 7. So therefore x equals to y minus 7 by 10. So you know that this become the inverse, but we write in form of x. So therefore f inverse x, which is nothing but g of x equals to x minus 7 by 10. This is your required answer. This is in form of y. Here I wrote in form of x. You can write in form of y also, like this also you can write. G of y equals to f inverse y equals to y minus 7 by 10. This also you can write, whichever you write, whether you write this or this, both are correct, remember. Question number 2 here, second question. You have a function f from w to w, these are the whole numbers, and fn is given in this way. Fn is n minus 1 if n is odd number, and n plus 1 if n is even number. Even, then we have this. Odd, then we have this. This is the formula for function given to us. We show that f is invertible. We show f is invertible. F is invertible. So we show that f is 1 1 and on 2. 1 1 and on 2. That's bijective. We show this much. If you can show that f is 1 1 and on 2, then f must have an inverse, and that's called an invertible function. That's the first part we do here. So now we go for 1 1. Now in definition of function, we have here odd number and even number. So we do in 3 different cases. So one case is, suppose n1 and n2 both are odd integers. Case number 2, n1 and n2 both are even integers. So we start with this. Suppose you know how to prove 1 1. Suppose f of n1 equals to f of n2. At the end we will show that n1 equals to n2. Here n1 and n2 both are odd. So this is n1 minus 1, this is n2 minus 1. So 1 1 will get cancelled, n1 equals to n2. So you shown that f of n1 equals to f of n2 implies n1 equals to n2 for every n1 n2. Odd integers, remember. So in this case f is 1 1. Here we are through. Now we go to case number 2. Suppose both are even integers. Again we start with the same supposition. Suppose f of n1 equals to f of n2. Now we are talking about even case. In that case, what is f of n1? That is n1 plus 1. What is f of n2? That is n2 plus 1. So it implies n1 equals to n2. So therefore what you have shown, f of n1 equals to f of n2, it implies n1 equals to n2 for every n1 n2, and therefore in this case also we are through, f is 1 1. Now third possibility here, that is one might be even, the other one is odd. Suppose n1 is odd integer and n2 is odd even integer. You may have reverse also, like this is even and this is odd. So obviously this being odd and this being even, n1 is not equals to n2. It implies, if I go for f of n1, now n is odd number, so if I use this formula, then this is n1 minus 1, which become even. This is an even, odd minus 1, so it's even. And if I go to f of 2, here n2 is even. If I write plus 1, so this become odd. So clearly this was odd, so this become even. This was even, this become odd. So f of n1 is not equals to f of n2. So this is another way of saying that f is 1 1. Whenever two objects are different, their images are different. So in this case also f is 1 1. So in all the three cases you have shown that f is 1 1. So this is 1 1 part. Now on to part. Check for on to now. For on to. Now to check on to here, it's not a big task because the function is defined on w. You recall whole numbers means positive integers with 0. So w is the 0, 1, 2 and so on. Positive integers with 0. So if I start finding images here, suppose if I find f of 0, 0 is even, so you have 0 plus 1, this is 1. If I go for 1 here, 1 is odd number, so 1 minus 1, 0. If I go to 2, 2 is even number, so 2 plus 1, 3. If I go to next 3, 3 is odd number, then 3 minus 1, 2. If I go for 4, 4 is even number, so 4 plus 1 is 5. If I go to 5, 5 is odd number, so 5 minus 1 is 4. So you observe 0, 1, 2, 3, 4, 5. You will get all numbers. So what is RF here? Range of the function. That is again 0, 1, 2, 3 and so on, which is again W. So what you have shown here, you can say that here RF equals to range of the function equals to W, which is codomain, and therefore f is on to here, function is on to. So function is on to, your function is 1 1 in all the three cases. So function is 1 1 and on to both. So it becomes bijective function. So f is bijective and therefore f inverse exists. So we find f inverse. This is the question. So recall again f, f of n is here n minus 1 if n is odd and n plus 1 if n is even here. So we have two possibilities. So we find inverse in form of two cases here. One case, that is n is even here, or let's take n is odd here. In case number 2, second case, that is n is even integer here. So method to get the inverse. Suppose f of n equals to y. Now if n is odd, then you have this formula. So n minus 1 equals to y. Make n as a subject of expression, you know. So y plus 1. So in this case, what is f inverse n? That is, instead of y, we are going to write n here, n plus 1. If n is odd, remember. That was the beginning. So this is the formula for inverse if n is odd. Same way, go to this. Suppose f of n equals to y here. Now here n is even. So n plus 1 equals to y. Make n as a subject of the expression. So y minus 1. So therefore f inverse here equals to, instead of y, we just write n. So here n minus 1. If n is even, remember, that you have used. So finally f inverse n equals to, we have n plus 1 if n is odd, and f inverse n is n minus 1 if n is even. So this way we have the inverse of the function here. Now here, if n is odd, you can see, then this become even, odd minus 1. So y becomes even. So if n is odd, then this y is even. Now if n is even, then n plus 1 is odd. So here y becomes odd number. So here I have replaced y by n. So this is like y. So instead of this, if I write, for example, this one, so it would be more clear. So f inverse, let me write y only. So here y is even. So y plus 1 if y is even here. N is odd, then y is even. And here, if I write this one, y minus 1 if y is odd number. Now you look at this is same as the given function. If odd number, then y 1 minus 1 formula, even number, then plus 1 formula. So you can say that f inverse is just f. So this is the final conclusion. So inverse of a function is itself here. So here you are given a function and you are asked for f of fx, that is a composition with itself. So f of fx equals to f of, write the formula for function, which is x square minus 3x plus 2. Now again f. So what we'll do, in the formula of the function, instead of x you write this. What is the formula for the function? That is x square minus 3x plus 2. So in this, in place of x, you are going to write this inner expression. So this would be x square minus 3x plus 2 the whole square minus 3 into x square minus 3x plus 2 and plus this 2. Now you simplify, this is your answer. I repeat this step. What I did here, you imagine this is like, for example, p. So this is like f of p, small p. This bracket is small p. Now what is f of p? That is p square minus 3p plus 2. Now again, in turn, you place the value of p. What was p? That is x square minus 3x plus 2. So x square minus 3x plus 2 the whole square minus 3 into x square minus 3x plus 2 and simplify. This is your answer. Fourth question, which is an important example. You have a function f from real numbers to open interval minus 1 to 1. Open interval minus 1 to 1. function is given by x upon 1 plus x. We are asked to show that f is 1 and on to both. 1 and on to both. That's what we are asked. So first part is 1 part. 1 part. So you start with this. Suppose let's start with this. x1 is not equals to x2. For every x1, x2 belongs to real numbers. That's a domain. Two numbers are different, then clearly if you find x1 upon 1 plus modulus x1, if you find x2 upon 1 plus 1 upon modulus x2, these and this might be equal, remember, because this may be 2 and minus 2. In that case this is 3, this is 3, but numerators are different, so clearly this 2 would be different. So f of x1 is not equals to f of x2. So what you have shown, whenever elements are different, then their images are different for every x1, x2, and therefore your conclusion is f is 1 function. This is your conclusion. F is 1 function. This is a 1 part. Now on to part. So I'll try to find the range directly. You know, for every x real number, if I find x and modulus x, then this is always greater than or equal to this. And even if minus x is again less than or equal to modulus x is always greater than or equal to both of this. I'm interested to find this one, x upon 1 plus modulus x. So I need 1 plus modulus x. So I'll add 1 only on right hand side. If I add 1 on the right hand side, then this 2 need not be equal. So this would be greater than this. I'm just adding 1 on the right hand side. So this is just greater than minus x. I need this one in the denominator. So x upon 1 plus modulus x is less than 1, taking this one in the denominator, minus x upon 1 plus modulus x is again less than 1. Now I need this much only, so I will multiply with minus sign here. So x upon 1 plus modulus x, you know, when you multiply with minus sign, inequality will be reversed. So this greater become less sign become greater sign. So if you combine these two, you can say that x upon 1 plus modulus x is less than 1 and is bigger than minus 1. So now what is this? This is fx. So fx is less than 1 and greater than minus 1. So you can say that range equals to open interval minus 1 to 1, which is equals to codomain. And therefore f is onto. I did this way. You can do like this also, or by taking fx equals to y also can prove. By taking fx equals to y also you can do, but this is comparatively easier here, so I did this way onto part. We want to show that this function defined in this way is injective. Injective means 1. This we want to show. So we start with this. Suppose f of x1 equals to f of x2 for every x1, x2. It implies your x1 cube equals to x2 cube. So you take the cube root on both the sides, so x1 equals to x2. So what you have shown, f of x1 equals to f of x2, it implies x1 equals to x2, and this is true for every x1, x2, and therefore f is injective. Injective means 1. Or You can do like this also, remember, or you can do this way also. Suppose x1 is not equals to x2, it implies their cube must be different. If numbers are different, then cubes are also different. Now what is this? This is f of x1. What is this? This is f of x2. These two are different. So what you have shown, whenever elements are different, their images are also different. And this is true for every x1, x2 from the domain. And therefore f is injective. I've shown both the ways. You can use any one of these two, whichever you like. Both are standard techniques, remember. So in the 8th question, you are given one set here, P of x. It is a set of all subset of x, if you remember, power set 11 standard. Relation R in P of x. So here members of these are subsets of x. So we take two members. Let's take A and B. These are the subsets of x, remember, which are in fact the sets. Let A and B be two members of P of x. And this is given to you, A related to B, if and only if A is a subset of B. This much we are given. This is given to us. We say that two sets are related if one set is a subset of the other one. This is given. Now question is here to check whether relation is equivalence or not. To check R is an equivalence relation or not. Equivalence relation, equivalent relation or not. This is the question. So we need to check whether this relation is reflexive, symmetric and transitive or not. Now here first one, you know, for every set A, set is always related to itself. So you can say that A related to A. This is a standard property on sets. So therefore what is the conclusion here? R is reflexive. This relation is reflexive here, remember. For every member of the set is related to itself, so it's a reflexive relation. Now, if I recall from the sets, if A is a subset of B, always not necessarily B is a subset of A, remember, need not be true. One set is a subset of the other one, reverse need not be true. Like, let's take A equals to, for example, I'll take 1, 2. And B equals to, let me take 1, 2, 3, 4, for example. So here A related to B, because A is a subset of B, as A is a subset of B. But you can see that B is not related to A. Why? Because B is not a subset of A. So therefore, what's the conclusion? R is not symmetric. R is not symmetric. It's like divides the relation, divisibility. This is same as, this relation is same as, just to remind you, this divides the relation is same as, the subset relation is same as divisibility, if you remember. Divisibility relation. You recall beginning of this chapter. For example, 1 divides 2, but 2 doesn't divide 1, but 2 does not divide 1. You know this. It's like that only. Just to remind you, does not divide 1. 1 related to 2, but 2 is not related to 1. So here only you can say that this is reflexive but not symmetric, and therefore it is not an equivalence relation. Now let's check the third, transitive property. So for transitive property, suppose you know what is to be done. Suppose A related to B, B related to C, and you need to show that A related to C. If you remember, transitive, this we need to show. Now what's the meaning of A related to B? A is a subset of B. What's the meaning of B related to C? B is a subset of C. Now this is very standard property of the set. If A is a subset of B and B is a subset of C, then you know that A is a subset of C. So here A is a subset of C. And therefore you can say that A related to C. And therefore here this relation R is transitive. And therefore you can say that R is reflexive, not symmetric and transitive, and R is not an equivalence relation. It's not an equivalence relation. That was the question. Is this equivalence relation? The answer is no, because it's not symmetric. Next question, 9th question. You have a non-empty set X. This is not an empty set. Binary operation is given on P of X, power set of X. So here members are set of subsets of X, you know. So your members are subsets of X, power set of X. And binary operation asterisk given by this A asterisk B. Why we have taken capital letters? Because these are the members of Px, which are sets, equals to A intersection B. This is our standard intersection operation on sets. You know that this is commutative and associative. Now question is identity element. That's the first question. Identity. So here X is like universal set, you know. X is like universal set, largest set, a universal set. And recall, this is always true. It's like standard property for every set A intersection X. If I do reverse, X intersection A, these two are always equal, and answer will be that set A only. So this is like E, you know this, we have discussed. So here identity is X. Here identity is X, remember. You recall such things you did in sets. A intersection universal set intersection A equals to answer is A. Such things you did in 11th standard in sets. But here instead of universal set U, you have X. This is a smaller set. So A intersection X equals to X intersection A equals to A. So here identity is X. This is identity element. Now you are asked for inverse also. Next is here invertible element. So you recall here by definition A asterisk, you find some another set B asterisk set A again. The answer should be identity, which is here, you know, X. That is A intersection B equals to B intersection A equals to X. This is identity, remember. This is the definition of invertible element. B is said to be inverse of A, if you recall. A asterisk B asterisk A equals to identity. Now you want B here, remember, inverse of A. You know that this is possible only when these two are equal and equals to X, otherwise you won't get. So this is possible only when A and B both are X, otherwise you won't get X. If these two are different, your answer won't be identity. So therefore you can say that X intersection X x intersection x equals to x. So you can say that inverse of x is itself, and it is possible only for x, not for other members, remember. Next question number 10 here. You are given a set here. A has these n members, 1, 2, 3 up to n. So this is one set A which has these n members, 1, 2, 3 up to n. The same set here, A 1, 2 up to n. So you want the total onto functions. This is indirectly question of permutation. Now one member can be associated with any one of this. So here member 1 can be associated n ways. The element 2, now you want here onto function. So if I take 1 with, for example, here 2, then I cannot take 2 with this. If I do that, you would be having one extra member here. So in that case, it's not onto. Onto means every member should be covered. If I take 2 again with this, then you will find one extra member in this codomain. In that case, it's not onto. So I cannot take 2 with this. So now for second member, you are left with how many objects? n minus 1. So 2 can be associated n minus 1 ways. 2 members already taken. So 3 can be taken how many ways? n minus 2 ways. And so on. If I continue that way, for n, you are just left with one possibility, one way. So if you remember counting principle here, so therefore by counting principle, total functions onto functions equals to product of all this n into n minus 1 up to 1. And what is this? This is n factorial. So total onto functions is given by n factorial, remember. I repeat this. Onto function means there should not be extra member in the codomain. So if I take one first member 1, which you can take with 1, with 2, with 3 and so on with n. So 1 can be associated how many ways? n ways. Now one member you have chosen, for example you have chosen 2. Then 2 again you cannot take with 2. If I take 2 with this one, then you will find one extra member in this. So in that case it's not onto. So for second member I would be having how many possibilities? 1 less, that is n minus 1. So for 2 members, 2 objects you already used. For third member you are left with n minus 2, and so on. If I continue, for the last member you are left with just 1 possibilities. So total number of ways by counting principle, that's a product of all these n ways, n into n minus 1 up to 1, which is n factorial. So total number of onto functions from set to itself is n factorial. Next 13 number, here you have a non-empty set like earlier questions. Px is the power set of x, that is all subsets of x. One binary operation defined in this way. Now first you are asked, show that identity E equals to, you are asked to prove that identity E is 5. We prove this. This is what we are asked. We prove this much. So you find A asterisk E, which is E is 5 here, union 5 difference A. You know that this is A union, this is 5, so answer is A. Same way, if you find E asterisk A, so it is E means 5 minus A union A minus 5, so that is again 5 union A, so which is A. So you can say that A asterisk, here E is 5, here E is 5 asterisk A equals to A, so E equals to 5 is proved. If you recall, this is a standard symmetric difference. This is called symmetric difference from sets. This is called symmetric difference. Now next, here also, if you find A asterisk A, which is as per definition A difference A union A difference A, which is phi union 5, which is 5. Now what is this? This is identity. So what you have shown, A asterisk A equals to A. So you can say that inverse of A is itself. For every set A, this is true, remember. So we have shown that here phi is identity, and for all A in Px, the inverse, it's itself invertible and itself. Remember, this is very well known property. A star A is always identity for this operation.